I'm going to talk about an experience paper, which is focusing on deploying network cost alignment based on the application priorities, specifically for storage services. Again, this is joint work between Google and University of Toronto. So it goes without saying that network delays is really critical for performance purposes for network services. Service performance, if they experience heavy congestion within the network, then you will see severe degradation in terms of SLOs, violations, and so forth. So it turns out different applications, and depending on the RPCs, it has varying degrees of sensitivity to the network latencies. For example, there are latency-sensitive applications, and there are also throughput-sensitive applications. For the latter, the bandwidth is more important rather than the latency. So prior work, there's a lot of research done on mitigating network congestion. But unfortunately, it's not possible to completely remove network congestion. Occasionally, you do have these huge traffic bursts, right? And when those traffic patterns occur, what happens is that there is a buffer buildup within the switches due to the finite amount of buffer memory space. And because of the additional queuing delays, sometimes you can experience packet loss. And that leads to degraded performance. So an obvious way to address this challenge is using quality of service, QoS bits, that are embedded in the packet header and to perform some kind of differentiation. So this differentiation allows services to offer different SLOs and latency guarantees at a per application basis, and also we will show you later at the RPC level. So what happens is that commodity switches today actually already implement the weighted fair queuing. So based on the QoS bits, it classifies the traffic into different QoS queues, and each QoS level gets different amount of weights. And the weights corresponding to the amount of scheduling priority it receives. And that also has implication on the buffer memory allocation. So at time of congestion, traffic with higher QoS settings will get likely more priorities because it has higher QoS weights associated with that QoS class. So if you look at storage applications at Google, it's composed of lots of many RPCs or remote procedure calls. And if you look at those RPCs, they actually have different levels of demand in terms of network requirements. Some are delay sensitive, as I mentioned before, and some require higher throughput. And the illustration here shows for 3 different storage systems, there are 3 different types of priorities. As you can see, the distribution of these priorities vary depending on the storage application itself, right? Interestingly, you see system 3 only uses primarily 2 types of priorities, and they use very little of the 3rd priority. And we'll talk about that service in more detail later on. So I want to just briefly introduce to you Aquitas. This is based off the SIGCOMM 2022 paper. And in that paper, it talks about 2 components. And we are going to primarily focus on the first component, which is aligning priority class with the weighted fair queuing QoS levels at the granularity of the RPCs. Right? It sounds relatively straightforward. Basically, what we are looking at is taking the application priorities and map that to the QoS, set the QoS accordingly for the RPCs based on that priority. It sounds fairly easy, but it turns out there are a lot of challenges during the deployment of that mapping. So when we do the mapping of the priority to network QoS, we perform that at RPC level. So we have that mapping information. And for this deployment, we focus on primarily storage systems because a huge amount, around 75% of traffic, actually come from and are destined to storage services. So that's why we think we start with that, which will handle a huge fraction of the traffic. So for this work, we actually looked at 3 classes of RPCs, and each of them mapped to a correspondingly a QoS level, starting with best effort. This tend to be kind of no strong guarantee at all. It's a scavenger traffic class, and it naturally maps to the lowest QoS. And the non-critical kind of traffic typically is throughput sensitive. It maps to the medium QoS level. And finally, the performance critical, which is the latency sensitive traffic class, mapped to the highest QoS. So let me just briefly introduce the Google storage system architecture. What I've shown here is a diagram of clients interacting with upper layer storage system, for example, Bigtable and Spanner. And the upper level storage system have a commonly shared lower level storage system, the back-end system. And this common layer allows them to talk to the back-end storage service and share the same kind of underlying library. So in the prior work, the focus in CCOM 2022, the focus primarily is on the upper layer to the lower layer storage system. Those red arrows, those RPCs are aligned based on the application priority. So in that paper, it didn't really look at these black arrows, which is the client-facing. So in this work, we are starting to look at handling the RPCs between the clients and upper half storage, because we really care about the end-to-end alignment, right? So if you look at the communication, you have to make sure all the RPCs are correctly aligned in terms of QoS setting, so that way you can get the expected performance based on the application priority. So for this work, we will make changes that the clients will directly observe the QoS changes. So therefore, clients could be more worried about potential performance degradation. And of course, we're also paying closer attention to the application performance metrics, such as RPC failure rates, retries, connection timeouts, and end-to-end latency metrics. So now let me talk about some of the deployment progress and challenges for this project. To start with, we thought about initially, why don't we just change all the traffic, set the QoS correctly based on the RPC priority, and just turn on the switch, right? But it turns out it's very difficult to apply Aquitas to all traffic simultaneously, because we don't really know the potentially unintended consequences because of the scale, tremendous scale, and diverse application needs. So a more conservative and safer approach would be going through a series of canary deployments. And for these deployments, what we are looking at is per customer, per region, and a fraction of randomly sampled target traffic. So that way we can really make sure that the changes are not affecting applications in a negative way, and we don't observe serious performance degradations or regressions. So this is exactly what we did, and we looked at cluster level or cell level at a particular region, and we sampled a fraction of traffic. And so one challenge we face is that Aquitas changes are often bundled together with many other ongoing production changes, right? These are live storage services, and any given point in time, there are ongoing improvements to the service, and potentially the changes we make could be mixed together with those changes. So it's very difficult to infer whether the change made by Aquitas by aligning the QoS settings are caused by the performance degradation. Is it caused by us, the Aquitas change, or by something else that is independent of Aquitas? So this sampling of traffic and allows us to do more meaningful statistical analysis. And when we do this control traffic versus Aquitas traffic at the same time, under the same conditions, this allows us to better understand, to be able to differentiate whether the changes are due to Aquitas specific changes, specific degradation to the traffic, or potential improvement is caused by Aquitas or not. So as I mentioned before, because it is customer-facing, so when we downgrade the QoS, meaning that change the traffic to set to a lower QoS, customers are naturally resistant, right? So they worry, hey, I already default to a medium QoS. If you want me to use a lower QoS for best effort traffic, does that mean I will experience significant latency and higher loss rate? So because of these concerns, we limited deployments to a small fraction of traffic to start with a very conservative approach. And really, we fully let it bake in and understand whether there is significant regression or not. Another aspect of this deployment is that we really need to pay close attention that the changes we make is not introducing additional resource bottleneck, because oftentimes the QoS setting is on the critical path of the application service. So let me just describe a particular use case of the Spanner service where it started off using only two priorities, the medium QoS and high QoS. The best effort case actually does not use any of the low QoS setting. So that is naturally introducing some concern to the customer that if they use the low QoS setting for their best effort traffic, does that introduce significant degradation in terms of latency experiences? And also what we've seen is that the misalignment is kind of spread out across all different cells based on request bytes and response bytes as well as the number of RPCs. So because of the extensive use of high QoS, the orange color, it turns out there's significant overloading of this particular QoS queue in the switches. So by setting the QoS to higher QoS level doesn't always guarantee you better latency, lower latency because of the overloading issue, because there is a limited resource in the switches. So pre-Aquitas, what we've seen is that between the non-critical priority versus the performance critical, as you can see, the difference is relatively small. Occasionally, we have spikes of non-critical. So the performance critical is this bottom line here. And what we're seeing, there are indication of priority inversion, meaning that sometimes the performance critical traffic actually experience higher latency than the non-critical traffic. And after we perform the alignment, as you can see, the difference is very obvious, right? The non-critical traffic clearly experience higher latency. The separation between the latency of these two classes is much more clear. And also, there is a reduction. What's interesting is that there is a reduction for both non-critical priority traffic as well as for the performance critical traffic, right? So this might be counterintuitive because some people may think that the low priority traffic may experience worse latency, but it turns out the load of the QoS queues is reduced, rebalanced out. That way, it's actually all you can win situation. It's not a zero-sum game. So after alignment, what we have is 80% of the response and request bytes are correctly aligned because we start focused on 4 of the spanner's largest clients. And what's important to note is that without Aquitas, application developers have to manually set the QoS, and oftentimes they make mistakes, right? So we can't really rely on them to set it correctly. So with Aquitas, even the pre-aligned Aquitas setup will be guaranteed to use the right QoS. So now I want to take some time to describe the key learnings that from this deployment experience. So it turns out we confirmed the prior Aquitas paper that we found priority is actually the correct network scheduling unit. Intuitively, sometimes people may think size might be, the size of the RPC may be the right indicator of what the QoS setting should be. But size information is not always available. And also, more importantly, RPCs and flows of the similar size can have different network requirements, can have different priorities. And our work actually shows production examples of traffic benefiting from scheduling at the correct priority level. Another interesting finding is that, as I alluded to before, lowering the QoS setting doesn't always imply increased latency. So this is actually not a zero-sum game. So there is a common misconception that setting the traffic to a lower QoS can lead to always significant RPC latencies. But this really depends on the load of that particular QoS queue inside the switches. Remember, there is this weighted fair queuing concept, and the QoS is enforced through that WFQ. And each QoS level has a specific weight assigned to it, and higher QoS tends to have higher weights, but that's a finite amount of weight. So there is a more theoretical justification provided in the paper. So we've seen here there is traffic for all 3 priorities. What we've seen here is that there's improvements for both medium as well as high latency, P99, the tail latency improvement. So this is improved across all 3 priority classes. And finally, I want to mention there is a benefit to incremental deployment, even though we can't really flip the switch to update all traffic. And there is this additional benefit, even though we only aligned a small fraction of the traffic. So in conclusion, Aquitas is actually a relatively simple scheme, It is all about setting the cost levels correctly based on the application priority. And it turns out there's this complex relationship between queuing load and corresponding latency. And with even incremental deployment, we already observed significant benefit in aligning the costs and seeing both the tail latency improvement as well as the median latency improvement. So we still have a couple of future directions we are working on. But with that, I'd like to take questions. Thank you.